Hey there, welcome back. Happy Monday. Anybody do anything fun and exciting over the weekend?
Hung out with the family.
Excellent. I got hung out with the family from the online Zoomers. Excellent. Always important. I did that too. Thank you. I should have taken a few minutes on Friday to debrief from the reflective writing assignment last week. It's been a weird 6 months for all of us, obviously. None of us, a year ago thought we'd be here today in masks and 6 feet apart doing this weird stuff. Me personally, obviously, I missed the end of last semester and all of the face-to-face interactions come with my job were sort of taken away at many of the good things about my job were taken away, and a lot of the bad stuff was still there. So I didn't appreciate that. Better this semester now that we're back somewhat in person and face to face for most of us. Positive things in my life have certainly come through. My youngest daughter was a senior in high school last year. Missed out on all kinds of stuff senior year wise, but my eldest daughter, who is a senior in college now, was a junior last year, came home in March, and we had never would have happened before. She was supposed to go to Africa on some fellowship that summer. That didn't happen, but we got to hang out for 4 months, just every day, all of us in the same house. We played, board games every single night. It turned out to be actually a very cool thing that never would have happened if the pandemic hadn't come along. So, as I am going through and thinking about all the things that are different and weird and I hate and don't like about what's going on now, I do have to step back and think about the things that have been pretty good, that have come about, that never would have come about without all this strange stuff happening. So I think it's important to keep that in mind. But none of that has anything to do with two-slit interference. So let's get back to two-slit interference. This is the diagram that we used to very simply and quickly derive the m lambda equals d sine theta for the location of the maxima of the two-slit interference pattern, right? You can, in 5 minutes with this diagram, derive this formula on your own. Our job now is so what does a two-slit pattern look like? This is what the two-slit interference pattern looks like. It looks a lot like a sine wave, except that instead of going from +1 to -1, it goes from 1 to 0. Or not even 1 being maximum and 0 being 0. Our job now is to derive the formula for that pattern. And that takes a little more than, we're going to do it 2 ways. One, I'm going to show you the traditional way that uses a whole bunch of crazy and random trig identities. The second involves phasors and is just geometric and it looks a lot easier. So that's our goal for today. Derive the equation for that formula in 2 different ways. Be helpful to pull out my notes though, because I'm not going to be able to do this off the top of my head. Okay, so what is our goal? We are going to, here is our geometry. We've got 2 incident rays incident on the same point. Those 2 incident rays came from the same source. They are coherent. They have the same wavelength. They have the same wave speed. They have the same frequency. The only way that they have the same amplitude. The only reason why those 2 are different is because there is a slight phase shift between one and the other, right? So these 2 waves, somebody's not muted on Zoom. Could you please mute? Thank you. Okay. So our goal is to add 2 waves without phasors. These 2 waves have some properties in that they have the same wavelength and frequency and amplitude. If you have not done the attendance thing, please do it in the next minute. I will close out. I wrote the number on the board if you can't read it. Okay, so we can write down the equations of these two waves. We know that wave one we can just write down the wave equation. Again, we're not going to care about, we just care about the amplitude of the wave. We're not going to write down any vectors. This is just the magnitude of the electric field as a function of time. E1, we've got some E max times sine of kx minus omega t. There is some arbitrary phase angle for the first one. We'll just arbitrarily set it to 0. E2, same thing, same amplitude, not a sim function, a sine function. Same kx minus omega t plus some phase shift phi naught. So that's going to represent the difference in phase between the first of these waves hitting there and the second of these waves hitting there. Okay, great. Let's make some shorthand. We're going to have to write this out a lot. There's no reason to really carry a lot of this stuff forward with us. Let's define EM equals 1. We can always set it back to EM at the end, but let's not worry about the amplitude is. We know it's the same. Let's define kx minus omega t to be A. That way, because that's not going to be changing either. And it's the same for both of them. Let's just define that to be capital A. Okay. So we're also going to need, so that simplifies these to sine of A and sine of A plus phi naught, which is simpler to write down. Okay. Okay, we're going to need some trig identities. Let's write them down at first. We're going to need sine, this is 1, sine of x plus y is equal to sine of x cosine y plus cosine x sine y. That's a trig identity. Here's another trig identity we're going to need. 1 plus cosine of theta, or let's just say x to keep these generic, equals 2 times cosine squared of x over 2. That's another one we're going to need. And the third one we're going to need is sine of 2x is equal to 2 times sine x cosine x. Okay, great. And I will just refer to those when we need them as we're going along. So we want to add these two waves up. The amplitudes of these two waves is a function of time. We know we've got sine of A, that's the first one, plus sine of A plus phi naught. Okay, by 1, we're going to use our trig identity number 1 to break that sine of A plus phi naught into sines, cosines, plus sine, cosines. Okay. So this we can write as sine of A, that doesn't change, plus this goes to sine A cosine phi naught plus cosine A sine phi naught. With me so far? Okay, all I've done so far is break up the second E2 into multiple sines and cosines using that first trig identity. Great. So let's group some terms here. We've got two, the first and second term both have a sine A. We can pull that sine A out. And this is sine A of 1 plus cosine phi naught plus cosine A sine phi naught. Just rearranging terms. Okay, now we can use trig identity 2 to replace that 1 plus cosine x with the 2 cosine squared x over 2. And we can replace that cosine sine, sorry, we're going to replace this sine here with this sine cosine combination. Okay, I'm going to do both of those things. So this is using 1, and this is going to be using 2 and 3. So the first thing I'm going to do is take that 1 plus cosine phi naught term. Sine A doesn't change, but this 1 plus cosine term goes to 2 times cosine squared of phi naught over 2 using trig identity 2. Yeah. Huh. So you're basically seeing what I'm seeing. That's just all there is. Do you need to see something that was above it? Is that, that's good right there? Okay. Yeah, I'm gonna go fast today. If you need me to slow down and scroll back and show me what I did before, this is the disadvantage of not having the entire whiteboard here. I could have all this thing down on, and you could see all of it at once. Here, you're gonna have to scribble down furiously and maybe think after the fact about how's it going along. All I'm doing though is using these trig identities up there to manipulate this thing and move it down. Okay, the second thing I'm going to do is expand this sign by using trig identity number 3. So I've got cosine A times, I've got 2 sine phi over 2, phi naught over 2, times cosine of phi naught over 2. And that is all using trig identity number 3. Taking that sine phi naught term and splitting it up into sines of phi over 2s and cosines of phi over 2s. We good? Okay. Great. Now we can expand terms and coalesce terms and combine terms. We've got, let's pull, in fact, both of these terms have a 2 cosine phi over 2. So let's pull it out. 2 cosine of phi naught over 2. And now we've got a sine A times, there's still 1 cosine phi naught over 2 term in the first term, plus cosine A, and we've still got a sine phi naught over 2 over here. And there's one final trig identity we can make and use, and that is use our trig identity 1 again to combine that sine, cosine, sine term back into just a sine term of the 2 things added together. So using trig identity 1 now, we will take this entire thing, and this just becomes 2 times cosine phi naught over 2 times this is sine of A plus phi naught over 2. Whew. That was a lot. 3 rather obscure trig identities though later, and a bunch of permutations. We've gotten to this thing. So that's a lot of work. Where did it get us? Cosine and a sine term, but wait. One of these trig terms is not like the other. One of these trig identities, one of these trig functions is the input to it is not a function of time. The cosine term out front, phi naught is not a function of time. Phi naught over 2 is not a function of time. That is a constant term. So what have we got here? This is a constant. What does that represent? That's the new amplitude of our function. We basically got back where we started from, which is a sine kx minus omega t plus some phase shift, right? The difference is instead of having a 1 out front, we've got a constant term out front that's not 1. That is the new amplitude of our sine wave, of our new wave. What is, the A is the same as before. That's right. Even if we included it, there would just be an Emax there, and it would still be the new amplitude times the old amplitude. It is the ratio. That's what you're right. It's not really the new amplitude. It's the ratio of the new amplitude to the old amplitude. Even if we had our EM in there, there would just be an EM here, and it would be ratio is how much stronger the new amplitude or weaker the new amplitude is compared to the old amplitude. That's right. A is same as before. And what is phi naught over 2? That's the new phase shift of the new combined wave. This makes sense. When we were looking at our combining phasors things before, when you combine two waves that are the same wavelength and the same frequency and the same amplitude, well, it's not a requisite aspect of it, you get a new wave that has the same frequency and the same wavelength with a different amplitude and a different phase shift. These trig identities have shown us how those new amplitude, what the new amplitude should be, and it's shown us what the new phase shift should be. And not surprisingly, the new phase shift, if your amplitudes are the same, is halfway between the old phase shifts. Maybe it's surprising, maybe it's not surprising. If you think about it, adding two, try it. Take a sine wave and then shift the sine wave. The sum of those two things is always going to be a new sine wave whose phase is exactly in between the other two, the two waves that you're adding together. And the amplitude will depend whether it gets bigger or smaller on how exactly how far you've moved it, exactly what that phase shift is. Okay. So this is not a general rule. So adding two equal intensity sine waves gives a new sine wave with the same frequency, but now the intensity, but new intensity, and the phase is halfway in between. This is not a general rule. If you have different amplitudes, that won't necessarily be the case. But if you have two waves that are coherent, same amplitude, same frequency, same wavelength, same wave speed, then this always happens. Is that your question? Correct. It will phi naught, the difference in wave phase between the two waves will vary as you move up or down the slope. It will not vary at a given location in the slope, which is why you get a constant amplitude there. But it will vary as you go up and down the slope, up and down the screen where you're intercepting this interference pattern. This is the intensity. Well, this is the strength of the electric field. And you know that you can get an intensity or an energy from the strength of the electric field. It's the square of it, plus some times some constants, but that's it. Right, so this is really we're defining amplitude of electric field, but that gives us, you square that and you get an energy. Okay, so can we do this easier with phasors? That's the question. I'll say, this was the easiest we could possibly make this. It's possible to use trig identities to do more complicated situations like with different amplitudes and different frequencies but it's a mess. It's really hard. Phasors, it's going to be easier to do this, the simplest example, and it's going to be not much more complicated to do these other complicated things we've talked about. that make it way better than the way we just did. Okay, let's with phasors now. One more time, this time with phasors. Set them to stun. Okay, so what do the phasor diagrams of these two waves look like? We've got our UV plane, and here's our two phasors. Let me draw this. I don't need all that negative space. Let me draw mostly positive space, and that's going to give me a little bit more room to work here. Okay, so here is, let's say, our first phasor. This is going to be kx minus omega t at some point. Here is our second phasor. Again, they have the same amplitude, so the length of those two phasors are exactly the same. This is going to be kx minus omega t plus phi naught, right? And the distance between these two phasors is the angle phi naught. Right? That's our phasor diagram for these two things. And the cool thing is, if we want to add two waves that have those two particular phasors, we can add those two particular phasors just by adding these things vector-wise. Add them head to tail, right? And remember how this works. The phase isn't constant. The phase is constant. The angle is constantly changing in time. But since these both have the same frequency, they both travel around together. And whatever new wave they make will also be a constant traveling around in time. We'll have this constant amplitude, but changing in phase as it moves around. Okay, so all we have to do is add these two vectors now. That's not too bad. Let's add them together. Let's see if I can do this. Oh yeah, that's nice. Look at that. I can't do that on the chalkboard, whiteboard. Okay, let's draw it a little bit bigger over here so I can get some room. Okay, so I've got my initial phasor. Here's kx minus omega t. And I've got a second one that I'm going to draw like right there. So my new wave, that represents the phasor of the new wave that is the combination of those two previous ones. If I can find the length of that phasor, I've got the new magnitude, I've got the new intensity, the new amplitude. If I can find the angle of that one, then I've got the new phase of my new phasor. That's really all you need to do now. So the new angle, so we know that this angle is phi naught. What is this angle? Doesn't really matter what we do with it. If we define whatever unit we define phi naught in. But if this angle is phi naught, in relation to phi naught, the first one, we define this one to be 0, right? There is no phi naught on here. What's that? It's not also phi naught. That's a good, I have drawn it badly here, and I had to, it kind of looks like phi naught because I had to come back. If I were to draw this better, it would be hopefully clearer that it was not phi naught. It would have to be phi naught over 2. I hope you can see that from the geometry. Maybe you can't see that from the geometry, and that's okay. But this has to be phi naught over 2. And that comes straight from the geometry. And it comes from the fact that we already knew it had to be that way in the first place. Even if we didn't, though, let's draw out this diagram, and then maybe it'll be obvious why it is. So let's draw this picture and make it bigger, this triangle, and make it a little bigger, and see if we can't make some heads or tails of it. So I'm going to draw it more on its side. That's not a bad way to go. We know that this angle is phi naught. We know that this has magnitude EM, this has length EM. We can draw a parallel line down this way, split this up into two right triangles, and hopefully you can see now that both of those have to add to phi naught over 2. Maybe not. Well, the whole all three angles of those triangle has to add to 180 degrees, right? Basically, you have to add. You have to add this, and both of those have to make it to the entirety of everything goes to 180 degrees, which is all the way around. And since we know they're the same, and we know that that gap is phi, it has to be that each of the individual ones are phi naught over 2. Okay, good. I see at least some people shaking their heads. It's good enough for me. Okay, so now what do we have? Let's call this whole thing L. This whole side is going to be L. L is one of the things we're going to want to know. L is the new, in fact, L is the most important thing. L is all we really need to know. We need to know what the new amplitude of this wave is. If we can figure out what L is, we've determined the amplitude of the wave and we've determined the energy, and that's really all we need in the intensity. The phase shift is unimportant for anything else we're ever going to do. It's kind of a cool add-on that it comes straight out of this, and you can see where it comes from geometrically, but really we care about what L is. And we have the goods to figure out what L is now, fairly simply. Because we've got this triangle, we know an angle, we know one of the sides, we can get the second side. So, this is the triangle we're interested in here. I'm going to draw it in red. So, what are we going to do? We know we want to know adjacent over hypotenuse. That's a cosine, right? Cosine of phi naught over 2 has to be equal to L over 2, half of that length, because we split the triangle into half, divided by EM, our original magnitude of our electric field. Now I do a solidus thing for L. What is L? L is, I guess the cosine phi over 2, the phi over 2 matter because we needed it for the cosine, and that will matter on what our new amplitude is. So L is, what is it? It's 2 EM times cosine of phi naught over 2. It just comes straight out of the geometry of the phasors and adding them two in together. And if you look, 2 EM times cosine phi naught over 2 is exactly what we got up here using all those crazy trig identities for the amplitude. We didn't have the EM in there. It was easy enough to put it in here. We didn't have to think about it. We get it straight out. That is our new amplitude, the length of that vector. And we get the rest of this because we know what the new phase is. We could write that whole thing down without having to know any trig identities or having to go through any of that hassle that we just went through, just from the geometry of the phasors and adding them together. It's a very powerful tool, an easy tool for adding sine waves and cosine waves together. So we know now that E1 plus E2 is the new length of this 2EM cosine phi naught over 2 times sine of, we still have our kx minus omega t, but we know that the new phase is phi naught over 2. We can just write it down without even thinking about trig identities. And you can see, even if you were to make those lengths, those EM, the lengths of those phasors different, the amplitude's different, it wouldn't be too complicated a geometry problem to figure out what the length of the new vector would be, new phasor would be, and what the angle of the new phasor would be. Okay, you get even more savings with more complex problems, and that's my point. Okay, great, that's it. We have just derived in two different ways the the equation of this particular line, that particular curve. It's still a sine wave. It still has the same frequency and wavelength as before. It's got a different amplitude, and it's got a different phase. We don't even care about that, really. It's only really the amplitude that matters. Okay. Recall our approximations. And I should go back to, oh, well, that's okay. One of our, basically, our approximation was that L, the distance from the slits to the screen where we're measuring these intensity patterns, is much, much bigger than the distance between the slits, D. That made it so that we could specify a single angle from both slits. And now it makes it so that we can assume that the intensity that is received at the slit will be the same for both. As you know, that's not truly the case. Let's go back and see our geometry again. So at this point P, both of these, it should be that the same power, the same energy is emanating from both of these slits, but it's spreading out in a uniformly spherical way. So it is the case that the intensity as seen from point P of the top slit is going to be a little bit higher than that from the bottom slit because it's a little bit closer to the top slit. We're going to shove that complication also under the rug and assume that if L is much, much bigger than D, that difference in intensity is so small that we can ignore it. When you're going to do this in lab this semester, the two-slit interference lab with sound waves. And so when your data doesn't quite agree and you're not getting quite the right intensity pattern, one of the excuses you can use is, well, you assume that L is much, much bigger than D when you derive the equation that you're using to fit your data. And it might not be the case for you. In fact, your D is going to be something like 10 centimeters and your L is going to be something like a meter. And that's bigger, but maybe it's not double greater than sine greater than. So, just keep that in mind. Okay, great. So let's do an intensity formula. So here's our geometry again. You've got their two slits. You've got a screen over here. Here's some function y. We'll call this 0. We define some point P up here that we're interested in. We can draw a line from both of them. We know that this angle is theta. We know that this is some delta here, which is the difference in path length from slit 1 to slit 2. So we know that this is delta L. So we know that delta L is d sine theta. We've already written that down. We know the phase difference, delta phi, is equal to 2 pi times delta L over lambda. Why the 2 pi? Delta L over lambda will give you how many waves there are difference in that path length, right? That'll give you delta L over lambda is 2. There are full 2 waves in that. There are 2 full more waves from the bottom path than from the top path, right? Delta delta L over lambda is 1.5. There's 1.5 waves in there. What does the 2 pi give us? It turns it into an angle. That's right. It turns this into an angular phase shift. That's right. Okay, so we can rewrite this. We know what delta L is. This difference in phase shift, or we could just call it phi, the phase shift between the two waves, is 2 pi over lambda times our formula for what delta L is, d sine theta. So this is exactly what we had before. We know that E1 is EM times sine of kx minus omega t. We know that E2 is EM times sine of kx minus omega t plus this phi, delta phi, whatever you want to call it. And we know we've already done this twice, derived it twice, that the sum of those two is 2em times cosine of delta phi over 2 times sine of kx minus omega t plus delta phi over 2. We do care about the new intensity. We don't care about the new phase shift. All we really care about the new amplitude because we care about the intensity. That's really what we're trying to derive. The phase shift means nothing to us. We're always going to be averaging over an infinite number practically of waves. We don't care whether they're shifted a little bit or not. Okay, so you might remember the intensity formula. The intensity formula, C times epsilon naught over 2 times E squared. Great. So we know what E is. We can just square it, and that gives us our new right. So this is C times epsilon naught over 2 times 4 EM squared cosine squared kx minus omega t. And then there's some 1/2 phi naught. Again, we don't really care about this. Delta, we'll call this delta phi. Okay, but what is C epsilon naught over 2 times E squared? What is that term? C epsilon naught over 2 times E squared. Oh, you're right. I thought, wow, that's a mistake in my notes. And it wasn't a mistake in my notes. It was the amplitude. This should just be delta phi over 2. Thank you. You're right. We don't, that's still there, but, and in fact, all we really care about is the RMS of this amplitude. There really should be a 1 over square root of 2 here to go from RMS electric field to maximum electric field. But that's really all we care about, right? So to go from max, we really need a factor of 2 here also. But it's not going to matter in a bit. And so I'm going to shove that detail under the rug also, and you'll see why it doesn't matter in just a second. Because the real question is, what is this? What is that C epsilon naught 2 over 2 times E squared? Of? No, the new wave has that 4 times EM squared times cosine squared term. I'm just thinking about the C epsilon naught over 2 times E squared. That's the intensity with the 4 times cosine squared is the intensity of the combined wave from both sources. What is it without the combined wave from both sources? The original. What do you mean by the original? You're on the right track. Yeah. That's one way to think about it. The way I want you to think about it, yeah, go ahead. It would be the light source. So what do you mean by the light source? Right. So you're thinking about beyond the slit now. Yeah. So that will depend on how far the slits are from the light source, because it will be expanding in a spherical way. This will depend somewhat on how far the screen is exactly away from the slits. You can shove all of that stuff and ignore it if you think about the intensity that would be on that slit from a single slit if there weren't the second slit there. Right? If there weren't the second slit there, you would still have the same intensity from that first slit. It would be going down as you went up because of distance differences. But this is basically the intensity from a single slit with the modulo 1 over square root of 2, which gets squared, which isn't going to matter because that's going to be in here too. And we don't even really care about that too much. This is the intensity of a single slit at that point. The intensity of the light from one of the slits at that point. From, I'll say, one slit. Because we're going to use single slit to mean something different later on. So, what's the difference between these two? There is a factor of 4. Well, let's write it down. We can think that the intensity from a single slit, let's call that I naught, right? If we were to cover up one of the slits, the intensity there would be I naught. Okay? Therefore, the new intensity is just 4 times I naught times cosine squared 1/2 delta phi. And that's a much more useful way of thinking about this, because we're not really interested in what the electric fields are. We're not going to be measuring any electric fields, but it's really easy to do an experiment where you just cover up one of the slits and see what the intensity is, open the slit and see what the new intensity is. That's almost always I naught is what you're comparing this to anyway. Almost always it's I naught that you're going to be thinking about this. What is the intensity from a single slit? Okay. What is this factor of 4? This is an interesting number. Why is there a factor of 4 there? This you can logic out a little bit geometrically. Why should there be a factor of 4 there? Right. So that one factor of 2, I'll stop you there and you can go on in a sec. One factor of 2 comes from the fact that there's 2 slits. Wow, this is hard to say. I apologize. There are 2 slits shining on that point instead of 1 slit shining on that point. That will immediately should double the intensity. Where does the other factor of 2 come from? Yes, that's exactly the way to think about this. The other factor of 2 comes from the fact that the same total energy still must be hitting that screen, right? And yet some points are getting 0. And if you average this whole thing, In fact, you can kind of see it here. This is 2I naught. This dotted line is 2I naught. That's the intensity of two incoherent wave sources. If these things weren't experiencing interference, there would be a constant intensity at 2I naught, because that's the both of the light sources. That's the combined energy of both of those light sources. You still have to have the same amount of energy if we're interfering, but now some of it's getting removed from some places and added other places. And so it must be the case, since the sine wave has equal up and down from the average, that this peak is twice as big as the peak would be if you take all of that and spread it out. So the average, in other words, from here to here is exactly the same with this curve as it is with the dotted line, and it has to be, because we're conserving energy. That energy can't be created or destroyed. It has to be the same. But that makes our peaks, the amplitude, twice as great as it would have been. So the other factor of 2 comes from the fact that we've redistributed the troughs into the peaks, and that gives us another factor of 2. Excellent. So we also know what delta phi is. Delta phi is 2 pi over lambda times d sine theta. So we can write this whole thing out now. I, as a function of wavelength, a function of angle, is 4 times I naught times cosine squared of pi d over lambda times sine theta. You've got a sine inside of a cosine squared term. What is this craziness? It's completely crazy. This is one of the only places I've seen trig functions inside of other trig functions. By the way, and that is, so it's a cosine squared, and that makes sense because this looks like a cosine squared. Cosine goes from -1 to 1. Cosine squared goes from 0 to 1. Cosine squared has twice as many wiggles as a cosine term, but it goes from 1 to 0. And the 4 gives you the intensity out front. Here we've got the delta L over lambda, 1 at the first maximum, 0 at the central maximum, -1, -2, 1.5. All the half integers are giving you your minima. And there's your m lambda equals d sine theta. One word of warning. We're gonna do some. Next on Wednesday, we're going to spend some time trying to gain some intuition for what's going on here. But in the meantime, I want to give you a warning as you're doing homework for any of this stuff. When you have a sine inside a cosine, sometimes you're going to be doing the inverse of things and taking this apart. When you're doing the homework this week and next week, make sure your calculator is set to radians mode. Radians is the natural unit of angle, and you need to be in radians, especially if you're going to be taking inverse sines of things and putting them inside of other functions, other trigonometric functions. You will get it wrong if you're in degree mode. You have to be in radians mode when you're doing those kinds of calculations. So just a word of warning for this week's homework. And we'll work on building up some intuition for how this formula works on Wednesday. Have a good week. I'm going to put the box around this one because it's an important equation. Yeah, right. Well, you've got this is as a function of delta lambda over delta L over lambda, right? And so there was a 1/2 that canceled a 2 in the cosine squared term. That's right. That's right. So I think that explains that factor of 2 is important in mapping out where those things actually happen. Yep.